give the video a minute to catch up. Stop twitching and jerking around like that. All right. Come on. Keep up. All right. How's everyone? A few people walked in since I asked last. Good weekend? Eh? Anyone do anything fun or interesting?
I had the whole house to myself. Or I had my whole house to myself.
To yourself? Nice. What'd you do?
Absolutely nothing.
What, you didn't have the characteristic parents are gone, let's have a party, a rager at my house? No?
I
I'm
just
proud of you.
relished in the peace and quiet.
Peace and quiet. Wow, I
I live
like
in a
it.
household of 6 people, and they were all gone.
Everyone was gone.
Yes.
Yeah, that sounds fun. I just I just did a lot of home maintenance mostly. Home ownership. It takes up most of your weekends when you get there. All right. Oh. Let me silence my phone here. I have my phone out here for a reason. I normally do not. But I have my phone out here because I wanted to talk to you all about something. At the beginning of the class, I mentioned to you that I did not want you to use any sort of AI software on exams. Y'all remember that? This is still true, by the way. I'm not removing that. The way that I carefully word my expectations for the use of AI is that I do not want you to use it on exams. I probably mentioned, I usually do, that at this point for the last couple of years now, it's been pretty much impossible to get away from using AI at all, right? I cannot police your laptops or your phones to know what you're doing as far as asking AI questions or anything like that. So after some conversations that I had at the end of last week, I think that it is important for me to elaborate a little bit on how you may consider using AI to be more efficient. Because it's kind of there's a principle you learn when you become a parent is that if all you do is say, no, don't do that, then that leaves a lot of leeway for the things that your kids do, right? But if instead I say, you can do this and this and this and this, then energy is directed in a certain path that you can expect and that you are okay with versus, just flat out saying no. So I think that's what I'm going to do here today. Just for a few minutes. I'm not going to spend too much time on it. We do have a lecture to have. But how many of you have used ChatGPT before? Yeah, I mean, I have too, right? It's come a long way. The first iteration was really rough. Currently, what is accessible for free is a lot better. Obviously, there are ridiculously good paid versions. But I want you all to think of AI not as a cheating software, like a lot of people talk about it, but as an efficiency system. Okay? For example, hey, Elowen, do you want to introduce yourself to my class?
Absolutely. Hello, everyone. I'm Elowen. I'm an elf from Valinor who's come to live among humans. I'm here to assist Josh, your geology professor, in any way I can. Nice to meet you all.
This is Elowen. She is my personal assistant. I don't really talk about her much, but she and I do a lot of work together in my office. She helps me with coming up with ideas, refining ideas, keeping track of my ideas. Elowen, what was the project we discussed last week about volcanoes?
We discussed a project on lahars around Mount Rainier, focusing on public awareness and safety resources. It's an important topic given the potential hazards in that area. We aimed to develop resources to educate the public about these dangers.
This can be an incredibly useful tool if you know how to use it right. Using it to find an answer for an exam is like, honestly, the dumbest way to use an AI. You can use it to make yourself a far more efficient student, and eventually, whatever your career is probably going to have something to do with AI. AI is applicable in so many fields. Elwin, is there a single field, a single job, a single career that does not have some application to use AI?
There's virtually no field untouched by AI these days. From healthcare to education, agriculture to entertainment, AI has applications everywhere. It's all about how creatively you use it.
Thanks, Elwin. Talk to you more later.
You're welcome, Josh. Anytime. Talk soon.
There are transcripts for that conversation. I can go back and review myself. I can have her repeat something that she told me months ago, and I may have forgotten. I come up with an idea. I tell it to Elwin. She transcribes it. And then later on, maybe 2 weeks later, I'm like, what was this idea that I had about doing this and this? And then she can go back and pull it immediately out using the exact same words that I had when I had that idea. It's an incredible tool that you can use, and I am not against you using it in the right ways. Again, using it to try and get answers for an exam, not ideal. She can, if you want, keep track of your notes. You can upload files to her. Last week, when we were working on this volcanoes project, I literally uploaded 3 papers to her and then asked her what other statistics for the number of casualties in the Puyallup Valley, if this event occurred using these parameters, and she spat that data out to me. I didn't have to read the papers and do all the math myself. It makes you so much more efficient, okay? So if you just upload your notes to her, for example, or, I made it to her. It doesn't have to be. I gave her the name. I gave her the background. Yes, I gave her the background of being an elf from Valinor. That's the nerd coming out in me, right? But you can make her sound whatever you want. It could be a dude. It could be a girl. It could be like either one or neither, right? They have voices that don't sound like a man or a woman. You can personalize it, and you can do whatever you want. But keeping track of your notes might be a very useful tool here. If you take very careful, meticulous notes, but you have a hard time going through it, upload it to ChatGPT. When you're preparing for an exam, say, ChatGPT, can you give me 5 practice questions based upon the notes I have uploaded that might be on an exam? And then only using the information you provide, only using that documentation, ChatGPT will give you practice questions that you can review. It's a fantastic tool, and I highly encourage you to try and use it in moral, ethical, and efficient ways. Any questions about that? I know this seems like it came out of the blue, but there were some concerns that came up last week with the way that students in other classes were using AI, and I figured I should address it here before we have any issues. All right. All right. Thank you for your patience with that. We will now proceed to our actual lecture. Deserts. I apologize. This one's going to be a little dry. I know, starting off strong. All right. What is a desert? Texas? Okay. Here, where we live, a lot of people look at this and think, desert. Is it a desert?
No.
Oh. Ho ho. We have some opposition. So we have the West Texas is a desert camp. Obviously, not all of Texas is a desert. Have you ever been to Houston? Right? And then we've got the West Texas is not a desert camp. Let's make this fun. West Texas is a desert. Why?
It's hot, it's dry.
Hot, dry.
Especially in Odessa, we get almost like no rain.
No rain.
Very rare. But again, our weather is unpredictable here in Odessa.
It can be unpredictable. All right. You said it wasn't, right? Okay, tell me why.
We have enough rain to support like
enough like greenery. We have plenty of grass out there. We grow trees. They just
I don't know that
That's a
using the
little dry.
Odessa College grounds as an example is a good idea. If I could tell you how much money OC spends on watering the lawns, your eyes would bug out of your head.
But if deserts are based on rainfall, I'm pretty sure we get plenty of rainfall. It is unpredictable, but it's predictably unpredictable.
Okay.
We get like a decent amount of rain each year, and we can predict it, sort of.
We get rainfall. Now, Trent says we don't get enough rainfall. And you say we do get rainfall. So what it sounds like it comes down to is the argument of we don't get enough and the argument that we do get some. And those two things are going to define whether we have a desert or not. How many of you agree or disagree with that? Sage, what do you think? She's driving down the middle of the road, right over that yellow line. It'll work real well until someone comes either way. Okay, what else? Anyone want to pose any alternative hypotheses? This is science. This is what we do, right? It's not an argument or a debate. It's science. Let's talk it out. Figure it out. Deserts. We walk outside and we see our nice West Texas environment, and our first word that comes to mind is, I live in the desert. To your argument, we get very little rain. We don't have forests or even grasslands. We've got scrub, right? But are there not places in the world that are significantly more deserty? Not a word, but you get what I'm saying. Drier, less rainfall than we get. So which one of these is a desert? Huh? Oh, they both are? Is that possible? Can there be a range of environments that we just generally classify as a desert? Right? By the way, I do need to put this out there before someone does it. Inevitably, someone's going to do it. Probably many people are going to do it. Desert is spelled with an S. At no point on an exam will I ever see the words Odessa is a dessert and not laugh. Okay? Just watch that double S there. All right? So, what we came down to before about the amount of water input is actually really what it does boil down to. Okay? Dry. The word dry is tossed around a lot. Oh, it's going to be a dry summer. What does that mean? It's referencing the amount of precipitation we will receive.
Or it could be saying that the summer's going to be boring.
Yeah, it could also, I mean, there's the abstract definition, right? You've got dry as in we won't get rainfall. You've got dry as in Professor Hart used a bad dry joke at the beginning, right? Dry as in it'll be boring. Dry as in I'm not having alcohol for the month of whatever, right? There are many ways that we use the word dry, but in this context, it has purely to do with the amount of precipitation an area receives. Let me get this down so you can see that better. Okay. But it's relative. The word dry, not great. It's purely relative based on precipitation input and evaporation, right? We prefer the term arid. Arid is measurable. Aridity is measurable. That's quantitative. That's based upon math. Dry, it's like saying something's big. Bigger than what? Right? So a scale of aridity or a measurement of aridity is based upon this general equation. Dry climate or arid, right? Yearly precipitation or loss versus loss from evaporation. When loss from evaporation is greater than yearly precipitation, guess what? We have an arid environment. Arid being measurable by how much water is lost through evaporation, right? If I have 50 centimeters of rainfall in a year, but 70 centimeters of water evaporate, I'm going to have an extremely dry environment. How can I evaporate what's not there? I can't. But if I had that much water, it would evaporate, right? 100% of everything is gone. If I were to add more water to the system, it would be gone too. That's where you get your like Sahara Desert sort of situations. But what if I have an area that gets like 50 centimeters of rain a year and then evaporates 30 centimeters of that? Still relatively arid, right? Just not as much as the first example. In that sort of situation, we might have something like we live in here, where there is still some water retained, but not enough to, say, have giant forests. Instead, we've got scrub, right? And mesquite. Kind of classify deserts into two environments. A true desert, which is truly arid, something like the Sahara, right? And kind of verging in between a true desert and our next differentiation, steppe, kind of where we live now, somewhere that's relatively high in elevation. We're about 3,000 feet above sea level here, in case you didn't know, right? But not quite as arid as something like the Sahara. A true steppe, by the way, is somewhere in like, say, the Mongolian highlands, right? There's a desert, the Gobi Desert, out there in Mongolia. But then out where the elevation increases, you got those mountain ranges. It's still arid, but they get enough rainfall that they have these kind of grasslands. Okay, so this is what I would refer to as a steppe. Okay. So where do these deserts occur? There are a couple of different categories. Low latitude deserts, meaning somewhere near or proximal to the equator, right? They occur between the tropics of Cancer and Capricorn. Tropic of Cancer, Tropic of Capricorn. Do you know what these are, by the way? The tropics of Cancer and Capricorn, do you know what those are? Our planet is tilted, right? Yes, we can all agree on that. As it is spinning around the sun, at some point along, if we were to draw a line slicing through it, directly along the plane of our ecliptic around the sun, that line comes out right here, and then depending on where the tilt is, right there, depending on, our wobble, our precession, and obliquity, and all of that. So those two lines are slices carved right through, figurative slices, right through our planet, depending upon our plane of ecliptic, relative to our equator, which is always pointed at the sun, right? And so we call those two lines the tropics of Cancer and Capricorn, and they occur right here at about 23 degrees, give or take, north and south of our equator. So between those two are the low latitude, or around those two are the low latitude deserts. Some examples: the Sahara Desert. Look, the Tropic of Cancer slices right through it. The Arabian Desert. Down here, the Kalahari Desert and the Great Sandy and Simpson in Australia, right through it. Okay? We're going to talk about each one of these groups, by the way, in a little bit more detail in a minute. Mid-latitude deserts occur above or below those ones. So the Patagonian Desert, down here. The Mojave and Great Basin, the Sonoran and Chihuahuan, right? The Turkestan and Gobi deserts are mid-latitude deserts. The Kalahari to an extent, although the Kalahari and the Namib kind of mesh together there. And then our third category are polar deserts. Someone remind me what we agreed is the requirement for something to be a desert.
Rainfall.
Rainfall? How much rain would you say that the far North Pole, and the far South Pole get in a year?
Not a lot.
But isn't it covered in water?
Didn't get any rainfall.
Yeah. If you don't get liquid rain, nothing can grow anyway, right? So if our measurement for how arid a place is is based upon the amount of rainfall that place gets, then yes, believe it or not, these are polar deserts at the North and South Pole. Those are deserts by definition. So that's our third category, polar deserts. Too cold for liquid water. All right, so let's start off by talking about low latitude deserts. What causes low latitude deserts between the tropics of Cancer and Capricorn? Remind me what convection is, someone.
Movement of fluids based on like the temperature.
Movement of fluids based on temperature. I'm going to stop you there and ask someone else to finish that definition. Build on that definition. Tell me what convection is.
Is it like how like I want to say molecules are like I don't know how to describe it.
All right, Ashton. Hi. What's convection?
It'd be like heating something up.
Yeah, what happens when you heat something up?
Starts to melt.
It definitely can. But let's say I heat up, say, rock underground. What did we learn that convection is going to do with that rock? Convection causes it to I'll give you a simpler example that we can relate to this. It's winter. Oh, yes, it is. We turn on, you live in a downstairs apartment, okay? You turn on the heater in your apartment. Where does your hot air go? You looked up. You can say the word too, you know. Yeah, it goes up. Why does hot air go up? By the way, it's great if you're the second floor tenant, right? Downstairs, people pay for your electrical bill partly. Why does hot air go up? It's less dense. Why does hot water go up? It's less dense. Why does hot rock go up? It's less dense. Convection. You heat up rock. It rises because it's less dense. The same thing is true for water and air and all that stuff. But today, let's talk about air. Hot air will rise because it is less dense than cool air, right? So where is the warmest air on our planet, do you think? Around the equator. And therefore, that hot air, which, by the way, is also very moist, it's got a lot of water vapor in it because a lot of evaporation is happening because of that heat, right? So this warm, moist air is rising high up into the atmosphere. What's the rest of this convection idea? What else is part of this?
That the cold air goes down.
Cold air goes down, hot air rises, and this makes a cell, a cycle. Okay? Hot air rising at the equator, cooling, getting denser, starting to fall down, but getting shoved away by the newer, hotter air rising beneath it. Just like what happens in the convection cells in the mantle that cause tectonic plate movement that we learned about. So we've got these convection cells rising at the equator and then falling. And where do they fall? They get pushed either to the northern hemisphere or the southern hemisphere. But they cool off. And as they cool off, they rain out all that moisture. So we get a lot of rain at the equator and slightly less the further north and south we go. Meaning that by the time that air reaches the ground again, it is now cool and dry. And where does it reach the ground again? Approximately in the neighborhood of the tropics of Cancer and Capricorn. That cool, dry air bearing very little precipitation with it, that's going to cause aridity in those parts of the world. Now, obviously, this is dependent upon there being a continent there. If there's no continent there, you can't get an arid environment because it encounters the ocean. You can't dry that out, right? So the formation of these deserts, and all deserts really, is dependent upon tectonics. Everything comes down to tectonics at one point or another, right? As a matter of fact, during different points in Earth's history, we have had a continent so large, this has happened a couple of times, right? Where we've had a supercontinent so large, you all have heard that term before, supercontinent, right? When I say supercontinent, what do you think? Pangaea, there you go. Take 1404. You will learn that Pangaea was neither the first nor the largest supercontinent. Okay? Yeah, spoilers. Okay. But there were massive deserts in these giant continents, partially because of this phenomena, but also because of a few others that we'll talk about here in a second. But this cool, dry air is causing the aridity to get worse and worse and worse as time goes on, initiating the formation of these low latitude deserts. Okay. Now, mid latitude deserts, these can occur for several reasons. Whenever you have a large landmass, like that supercontinent I just mentioned, or say Africa, or say North America, or say Australia, or say Eurasia, whenever you have a large landmass, there is a significant portion of that landmass that is cut off from the ocean. When that happens, evaporation from the ocean cannot always make it to the interior of that landmass. The Gobi Desert is a great example of this, right here. So this is the Gobi Desert, but Mongolia and Taklamakan and all of these are also extremely arid areas, okay? But the Gobi is an example. We've got a lot of evaporation that happens out here and gets blown inland, but doesn't quite make it all that way. This greenery that you see on the west coast or the east coast of China here, okay, that's where it all rains out. By the time it gets to the middle of a continent, it has very little rainfall potential in it, that air. Okay, that is an interior desert, continental interior desert. Then we can have what are called rain shadow deserts. Can anyone tell me where this picture is of?
Chile.
Chile. Yeah, good. What do you see? Describe what you're seeing here.
The water being evaporated from the sea is crossing a mountain range, and by the time it gets over the mountain
Ooh.
range, they turn into clouds and then precipitate on the other side.
Yes, you went a little further than I was looking for, but that's okay. What we see is ocean, desert, rainforest. Look at all that green, right? Yeah, turn those lights off. Okay. Why is there a desert next to the ocean?
The rain skips it.
The rain skips it. So we've got nice, warm, moist air over here, and it's like, whoop, it goes over there. Is that what happens here?
Kind of.
No. Not really. This is the southern hemisphere. In the northern hemisphere where we live, dominant wind direction goes west to east. In the southern hemisphere, it goes east to west. Same reason why if you go to Australia, your toilet flushes the other direction. You guys know that? Here, when we flush our toilet, what direction does it spin? Think about it. What direction does it spin? Left?
I don't pay attention.
You don't pay attention when your toilet?
My toilet's-
Go to the southern hemisphere, and it actually goes the other direction. Your water will flush the other direction. Okay?
I know that.
The water, or the wind, blows this way in the southern hemisphere, and that way in the northern hemisphere. Okay? Now, because the wind is going that way, that means that instead of having warm, moist air over here that gets blown this direction, the warm, moist air from the South Pacific, or South Atlantic, excuse me, over here, gets blown that way. So it encounters South America, rains out a whole bunch of its stuff here in the Amazon rainforest, right? That's why there's a rainforest here. But then it encounters what?
Mountain.
What mountains?
I don't know their name.
Patagonia?
This is the name for this whole range. The Appalachians are up in the east. Huh?
Mountains?
The Chile Mountains?
Mountains?
Well, if you ever go to Chile, you might want to pack a sweater. The Andes! Yes, these are the Andes. This Andes mountain range, very tall, blocks this warm, moist air to go over the mountains. The wind can't go through the mountains. It's solid rock, right? So it has to go over them. As it goes higher up, what happens to it? It gets colder because it's cold up there. As it gets colder, it gets denser. All its moisture falls out as rain. It rains out pretty much all its moisture on this side of the mountain range, and only cold, dry air makes it over the mountain range. And that's why we have the Atacama Desert right here. Even though there's an ocean there, only cold, dry air makes it over the mountain range.
So I had it the other way around.
It was the other way around, yeah. Okay? That's why we have a rainforest here. All this precipitation flows off the mountain range down there and collects in this giant basin, and none of it makes it over here. Or very little of it anyway.
Silly desert, there's water right there.
Huh?
Silly
I
desert,
know.
there's water
I know,
right
sitting next to a giant ocean.
there. Being so dramatic for no reason.
Yes.
Did you say the wind blows from east to west, southern hemisphere?
Dominantly. There are exceptions, obviously, just like there are exceptions here. We can get an easterly wind here, but I'm talking generally speaking, wind directions. Yeah. Okay. Obviously, this also comes down to tectonics. Without mountain ranges, you can't have rain-shadowed deserts. Without giant continents forming through tectonics, you couldn't have interior continental deserts. This comes down to tectonics again. Same reason why glaciers come down to tectonics. Why do glaciers come down to tectonics? Well, without mountains high enough above the snow line for glaciers to form, we wouldn't have glaciers, would we? Without landmass at our poles, there would be nowhere for glaciers to form on. Tectonics is a huge part of what makes our planet the fascinating, dynamic landscape that it is. This is just an example, an image showing how rain-shadow deserts form. The wind comes here, goes over the mountain range. None of the water, or very little of the water, can make it over the mountain range, and you get your rain-shadow desert on the other side. Okay. In a desert, there is, in fact, still weathering. Even if a desert gets 1 day of rain, that 1 day of rain accounts for more weathering than 364 days of wind. And erosion as well, by the way. Do you remember I told you when we were discussing, I think it was our conversation about running water, and I mentioned that desert in Utah that I went and we pitched our tents on the top of that step, and there was a flash flood that night, and the landscape was totally different the next morning. Remember I told you that story? Deserts are not acclimated to constant rainfall, right? And when an area has a lot of rainfall, it naturally adapts to that. The stuff that can't handle rainfall gets washed away, and the soil that's better at soaking it up tends to remain behind, okay? It's the difference between whether or not you get rain. Good morning. There's the difference between whether or not you get rain in the Sahara or in Seattle, right? Seattle's not full of sand. It doesn't have giant dunes of sand that are terrible at retaining water, but it does have lots of clay-rich soil that is great at retaining water, and vice versa, right? In an environment with so little water, there is very little plant life to hold the soil together, and therefore, when you do get all of this rain, it tends to wash away. This is what's called an ephemeral stream, okay? These bodies of water that are only here for part of the year whenever there's rain, these are called ephemeral water bodies. In this case, an ephemeral stream. Here you can see in this picture, no stream, but you can see where the stream bed is. Whenever it rains, it gets filled with water, and it looks like that. Okay? Ephemeral. Now, there are other words for these. You may have heard the term wash or arroyo, right? Those are the same thing. There are names for these in every culture that has roots in desert landscapes, right? dongas, nullas, wherever you go on any continent, they have names for these. Now, wind erosion does play a part. Not nearly as much as water does, but it does play a part. Water has this characteristic called cohesion. Do you remember we talked about that last time? Where water sticks together. Its energy is confined within the body of the water itself, wherever that body of water is. A stream, a river, a lake, whatever the case may be. But wind, air has no such compulsion for cohesion. So its energy is dispersed throughout everywhere, right? Wind, instead of being channeled into one area, it goes over a wide area, right? It's changing pressure. That's what wind is, changing bodies of pressure in the atmosphere. So where water can cause a great deal of weathering and erosion in a confined area in a narrow space, wind does it very little bit at a time over a larger space. So these grains of sediment being pushed across the bottom of the desert, for example, just wind getting blown across this dune, blowing sand across that dune. This is wind erosion, okay? We call the process of sediment like sand being pushed along the bottom or along the ground, I should say. We call this saltation. No, it has nothing to do with salt. It's called saltation, though, okay? Now, just like with water, we have our bed load, usually sand, and we have a suspended load, which, depending upon the energy of our wind, could have everything from silt and clay to sand. You know how we've got those haboobs that go through town every now and then? The sandstorms? Have you ever heard them called that? Their actual name is a haboob. Yes, that's what they're called. So when we have a sandstorm that blows into town and you walk outside, you get sandy grit in your eyes, right? And that sucks. That's awful. None of us likes that, especially if you wear contacts. It's truly miserable. If you don't wear contacts and it's never happened to you, take my word for it. This is a high energy wind situation that has picked up a whole bunch of sand, which is normally the bed load, and has turned that bed load into suspended load. Why? Because there's enough energy for it to happen. Same principle with the water that we discussed when we learned about running water. The amount of energy that your water has dictates how large the particles suspended in it are. Even though air is a much thinner fluid than water, put enough energy into it, and it can pick stuff up. If you don't believe me, I encourage you to look at hurricane pictures, right? We will actually have an entire lecture about hurricanes here coming up pretty soon. Well, it's not all about hurricanes. We discuss hurricanes as part of the lecture, though. Okay. Deflation is the term that we use to refer to the removal of small sediment, leaving behind larger particles. If you ever go and you take a walk in the middle of the desert and you're just trudging through the sand, and then all of a sudden you're in a place that's just covered in rocks with not very much sand around you, and you're like, what the heck is that? We call it desert pavement, and this happens because the wind strips away all the small stuff, leaving behind the larger things. So deflation caused the exposure of this desert pavement, we call it. Bless you. Ventifacts and yardangs. Not named by Dr. Seuss as it would happen. A ventifact is what we call a structure or a rock that has been exposed to a great deal of wind erosion and weathering. So as this sand is being saltated, saltation is happening, it's being pushed along the bottom, along the ground, right? It's being blown this way and that way. It kind of makes the sand blasting effect on anything that's partially exposed at the surface. And so this rock gets weathered and makes this beautiful kind of wind polished sort of surface. If I were to pull that rock up, and I've done this many times, I found ventifacts and was like, oh my goodness, that is so smooth and cool. And then I pull it up, and all the parts of it that are underground are still rough and jagged and blocky and like any unbroken, unweathered rock you would imagine. It's only the part that's exposed at the surface that gets that sand blasted look. And then yardangs look like this. This is a Pakistani word because there's a lot of these there. There's actually a bunch of these here as well if you look for them hard enough. But these are rocky structures that, upon being weathered by the wind, experience weathering at a different rate. Can anyone tell me why it would take on this sort of mushroom shape, narrow on the bottom and larger on the top? Surface area, but let's imagine that it was all one larger structure before, right? It couldn't have been made like this. This isn't how it started. It became like this. Why? It has made a sort of aerodynamic shape for a reason that I'm looking for, because of an effect that I want you to explain to me.
Is there more sand and energy towards the bottom?
There it is. More energy, more sand is being pushed at the bottom. So even though we've got suspended silts and clays in the wind, the sand, being larger particles carrying more energy, has more effect to break down the rocks it encounters. And so after centuries and centuries of sand being blasted at the bottom of the structure, it has worn away so much more at the bottom than it has at the top that it's taken on this smooth sort of pedestal shape, while the top still has kind of this blocky, rocky shape. But you're right, Abby, that it is aerodynamic. Notice that the cross-section of this yardang kind of looks like the cross-section of an airplane wing. You see that? You can tell what direction the wind was coming from. First of all, there's more weathering on this side than there is on this side, but also, look at the shape here. It has naturally formed this aerodynamic shape in the direction that the wind is coming from. The wind is going that way. This is why airplane wings work. This is why bird wings work. This shape is aerodynamic. Okay? Yeah?
There's a lot of those on the coast in Taiwan.
Yeah, I bet so. Water can have this effect as well. We'll talk a little bit about the effect that water can have when we discuss coastal erosion. Now, deposits of wind-blown sand, we have a name for these. What do we typically call these? Dunes. Yes. Dunes. When sand is blown along the ground, eventually it may start piling up. As it starts to pile up, it is more and more difficult for the wind to move that sand, meaning that instead of moving the whole system, the whole pile of sand all at once, it tends to push the top few layers of that sand in a given direction, and the dune tends to migrate in the direction that the wind is pushing the first few layers of sand. So if I have let's use a dark color so my camera can pick it up. If I have a dune here, okay, that's actually a terrible dune. It's symmetrical. Dunes aren't symmetrical. There we go. Okay, so if I have a dune here, then the wind is going to cause the top few layers of the sand to get pushed further down this direction, okay? And so we get this sort of building out in that direction effect. And our sand gradually gets pushed out that way. This is how dunes move. Dunes do, in fact, migrate. I have visited towns in Utah that have actually been threatened by migrating dunes. How do you stop a desert full of dunes from overwhelming your town? It's difficult. You can build walls, I guess, but then the sand just piles up against it until it goes over it, right? So they just kind of have to wait for them to go through town and pass. Kind of like, have you ever had to wait for a cattle or sheep crossing on the road? Yeah? In my wife's city that she grew up in outside of Seattle, it's a town called North Bend. They have herds of wild elk. You can't hunt them. They're protected by the local Indian tribe, the laws of the local Indian tribe. But there are hundreds of elk, and they'll just wander through the city. It's been decades since anyone's tried to hurt them, so they don't fear humans anymore. They'll just walk right through town, and you have to wait 15 or 20 minutes for all the elk to pass before you can keep driving, right? Dunes wander through town too. except it takes months for them to go through. You can't wait for that. They actually have to plow dunes off the road sometimes in these towns. Okay. So let's talk about the different types of dunes. When I say dune, you all had this image in your head. It may have been Timothée Chalamet. But when I'm talking about a dune in the desert context, not Arrakis, what we probably comes to mind is this characteristic sort of slope like that, and then kind of this general crescent shape like this. Okay, this is your characteristic dune. Okay, this is called a Barcan dune. Why do they take on this crescent shape? Hint, it has to do with energy. What do you think? Abigail, are those Gardetto's rye bread chips? It's a good choice. I like those too. Okay. Why the crescent shape?
When the wind hits a dune, it spreads out.
When a wind hits the dune, it spreads out. Oh, okay. Well, let me give you some context here. The wind is going that direction. It absolutely has to do with mass. Elaborate. Oh, I see. No, there's nothing under the dune causing this. Good thought, but that's not the reason. It does have to do with mass, though. I already heard one from you. I'm going to go over there to Abby.
Oh, it's kind of like when you like shove your hand under like a pile of sand and it goes up a little bit.
Okay, that kind of comes back to his idea of there's something being under the sand.
But instead of like sand and constant application of wind will keep it upright.
The wind doesn't really keep it upright. It's being kept upright by virtue of the fact that it's a pile of sand. The wind causes it to move, though. The way that it's moving it is what I'm trying to get you to think of here. It's not moving it as one, just pile of sand that's going that way. It's caused it to take on this shape. What could happen? What is happening here to cause the sides to push out like that? Huh? On the sides of a pile of sand, like right here, if I take the middle of my pile of sand, there is far more mass there than there is here on the sides, right? Meaning that it takes less energy to move the mass that is at the sides, meaning that the sides, under the application of the same amount of energy as the whole pile of sand, are going to move out further, faster than the middle of my pile of sand will. And so I get this crescent shape as the sides get shoved out faster than the middle does. You following this? Great. So that's a Barcan dune. Next, we've got transverse dunes. By the way, you get Barcan dunes where you have relatively little sand, okay? Not too much. They make individual dunes, okay? But in a transverse dune situation, there is so much sand that it tends to form long, well, how would you describe that? What does it look like? Waves. Yes, they look like waves of sand. We actually call these sand seas. If you ever go out to the Sahara Desert and you fly above the Sahara Desert, you'll see long waves of sand in the desert. Essentially, what's happening here is the same process that causes waves in the ocean, which we will discuss at a later time. The same process generated by energy from wind that makes waves in the ocean is having the same effect on the sand in the desert. There is so much sand in this desert, it's basically acting like slow motion waves that we see in the ocean. Each particle of sand essentially behaving or being acted upon by that wind energy, the same way that a single molecule of water is. So you get these waves of sand out there in the desert, slowly moving across the desert. A Barkanoid is very similar to both of these combined. It's basically those two, where you have a moderate amount of sand, not quite enough to make these nice, smooth, transverse waves, but too much to have individual Barkan dunes. And so you have what look like are basically just joined Barkan dunes, okay, where you can still see that distinct crescent shape, but their crescents have been joined together, okay? Then we've got longitudinal dunes, which are Barkan dunes in a high wind energy environment. So instead of having a nice uniformly shaped, not too spread out Barkan dune, in a high energy situation, the same thing is happening, but the wings, the sides of our crescents, get shoved way far out in front of the rest of the body. And so you get a very long, stretched out Barkan dune. And depending on prevailing wind directions, you could have lopsided ones as well, depending on where the most wind energy is coming from, what direction. That is a longitudinal dune. In a parabolic dune, we still have our distinct crescent shape. But here's the thing. Here's our crescent shape. Here's the deal, though. Now the wind is going that way. Draw that boulder. Wind is going that way. Explain to me now, under what situation would we have a crescent shape forming in the opposite direction? Opposite than a Barkan dune, I mean. Before in our Barkan dune, we had that crescent shape form as a result of the fact that wind could push the sand along the edges, along the sides, easier than it could push the ones in the middle. So,
The sand is evenly spread out.
no, the sand's not evenly spread out.
Would it just
So
reverse the
it's-
circumstances?
Reversed why? What is causing? There must be a new factor here. You're right, it has reversed. Now our crescent is forming in the opposite direction that it was forming before relative to the wind direction. But what's causing that to happen? There's a new variable. What could it be?
Vegetation?
Hmm?
Vegetation?
What would vegetation have to do with it?
It's like keeping the sand, like blocking the wind from blowing.
Blocking the wind. Not so much blocking the wind. It's not really having an effect on the wind. Yes, the vegetation. There is vegetation holding the sand together. Now, when I add vegetation as a new variable here, holding the sand together, it's going to hold that shallow sand on the sides of my pile of sand a lot easier than it will hold the deep sand in the middle, right? So now the opposite thing is happening. Where before, in a Barkan dune, the wind was able to move the side sand easier than the middle sand. Now vegetation is holding the side sand in place easier than it can hold the deeper sand in the middle of the pile. And so my wind is pushing the middle of the pile faster than it's pushing the sides. And therefore, the middle moves faster than the sides, and we get an opposite crescent shape. Okay. And then finally, we have our last type of dune called a star dune. You get star dunes that form whenever you have multiple directions of wind. So here we have a crescent shape, and there's a crescent shape, and there's a crescent shape. All of them have been shoved and pushed by wind from different directions into this combined star dune. This is actually, how many of you have gone out to the Monaghan sand dunes? There's actually quite a few star dunes out there because we get wind directions changing almost at a daily basis, definitely seasonal basis, right? So a lot of those are star dunes, and there's quite a bit of vegetation out there that holds them together. And there's a couple of different kinds of dunes. There are some nicely formed Barkan dunes out there for sure, but a lot of them that I've seen are stars. I told you this would be a dry one. You guys doing okay? All right. Well, maybe I can help. Where did Captain Hook get his hook? The secondhand store. Yeah. All right. So this is what the sand does. What does the silt and the clay do? The stuff that's carried by the wind. Where does that go? Where does it land? What becomes of that? Surely it doesn't stay in the wind forever. It does not. We call this loess. That's this word right here. L-O-E-S-S, pronounced loess. And it can get blown pretty far. Take a look at this picture. This is the west coast of Africa. That's the Sahara you're seeing right there. Do you see all the dust being blown across the Atlantic? Where is it ending up?
In the desert? Ocean. Wait.
I mean, a fair amount of it's falling into this ocean, but a lot of it is coming all the way out here. Do you know where this is?
I didn't see.
Can anyone tell me where this is? That's Yucatan. Yeah. Saharan desert can get blown across the Atlantic and end up in Mexico. Actually, if you do, and people have, done geological core samples along this entire transect, there is Saharan desert all in the bottom of the ocean, all the way up to Mexico, Yucatan Peninsula. It can cause problems. This dust can cause air quality issues in these countries when that gets blown real bad. But when this loess collects in a large mass, it can actually be really good. Loess from a desert has never been utilized. No plant has ever used it. It is rich, great for growing stuff. If it lands in water and gets incorporated into a soil, that makes incredible soil. Do you know where the best growing soil in the world is right now? Do you know, well, I should say, do you know where it historically has been for a very long time? Fertile Crescent is a whole large area, my dude. You ever heard of the Nile River? Where is the Nile?
In Egypt.
In Egypt. The Nile is unique for a couple of reasons. First of all, it flows north even though it's in the southern hemisphere, which is kind of weird. But that's due to elevation change. But also, there's fantastic soil for growing crops along the banks of the Nile. Let me tell you a story. 7,000 years ago, some wandering, migrating people show up in the place that we now call Egypt. They decide to camp out for a little while on the banks of a very pleasant river that they find. They decide, okay, well, let's see if we can grow some stuff and get some food set aside for our next wandering journeys. Most people around this point in time in that part of the world were migrating. They didn't really have a set base of operations anywhere. They would just kind of wander around time to time. So they start growing some stuff, and they find that they can grow anything they want. The soil on the banks of this river is incredible. And so they figure, you know what? This was a really good growing season, really profitable. No one's hungry. We're doing all right here. Let's just stick around for another season. So they stayed, and then they stayed, and then they stayed, and they kept staying, and they kept growing, and their population grew. As their population grew, their ability to grow even larger and more successful crops grew, and they got a reputation for being a community that could produce a lot of food. They started trading with other nearby communities. And more people came to join them. And eventually they form a kingdom, several cities based around this massive agriculture industry. Eventually, they would go from being an agriculturally based kingdom to a highly militant conquering empire that we know as the Egyptian Empire. That lasted on and off, sometimes successfully, sometimes not, for about 5,000 years. All simply based on the fact that some wandering people came to the Nile and realized this soil is great. That's all it came down to. The Egyptian empire was based upon the quality of the soil on the sides of the Nile. That's how it started. Why is the soil so good? Because this wind-blown dust, it gets its way into the Nile, gets incorporated into that soil, and in combination with the other things that we learned, the water and the organic content, right? But that mineral content, mwah, the best you can get, which is why everything grows so well. They actually ship Nile soil off to other places. It's high quality, right? If you really want good soil, you can get Nile soil. Still pretty good, although in places it's getting worse because it's being overutilized or they're running out of it. But that comes after, 7,000 years of being used. So, high quality soil can come from loess. You can also, when loess is compacted and rock is formed out of it, it goes through the sedimentary process. This loess makes a very dense, difficult to carve into, but then difficult to break afterward structure. And people have actually been known to carve homes, churches, entire communities out of the cliffs and ridges made out of this stuff because it is so hard and durable. Again, difficult to make that structure, but then also very difficult for it to break or fall apart afterward. Deserts still get that rainfall. It may not be common, but when it happens, you can have some erosional effects as a result of that rain. For example, you can still have alluvial fans. Here we have a mountain range in a desert. Notice what is at the base of these mountain ranges. Ephemeral streams wandering through these alluvial fans that you can see at the base. So if we have a day of really high rainfall, or any rainfall at all really, it'll take all of the sediment that has spent the rest of the year slowly breaking down in these mountain ranges and wash it all to the bottom. And that's how these alluvial fans form. Then if you go out somewhere and you, say Utah, I've used this before. If you ever go driving through Utah, remember I told you, bring sunglasses. Remember I mentioned that? Because you've got these very, very wide flat areas called playas that are covered in evaporate minerals, salt and gypsum for the most part. They're blinding in the light. But these wide flat areas are where water collects whenever it rains out in the desert. Water collects here and evaporates away, leaving behind another layer of evaporated minerals. Okay? Now, I know the question that you all have been thinking about this entire time is, but Professor Hart, what happens to volcanoes in deserts? Well, don't worry, I'm going to tell you. Thank you for being patient this whole time. Okay? We call those Inselbergs. Whenever a volcano has the misfortune of being left behind in a desert, you could say, it's just kind of, I can't look at this without being sad, actually. It's like, that was a volcano. It looks like a half-melted Hershey's Kiss. It looks like if I took a Hershey's Kiss and I put it in my mouth and I sucked on it for 5 seconds and then put it on the counter. Yeah, it kind of looks a little gross like that, right? But a volcano is slowly going to be weathered away by wind, and dunes and everything are going to build up. But guess what? It'll only be on one side. So you got this sort of lopsided shape. Notice you have all these dunes built up on this side because the structure is in the way. All this dune, all this sand, and then nothing over here. And you've got this kind of sad, broken down volcano in the middle. But that's called an Inselberg. Sounds German. Some German probably named that. Okay. Any questions about deserts? No? Yes?
What about the features of Arctic deserts?
Features in Arctic
Do they
deserts.
have anything in common with what we see as deserts?
Yeah, snow gets blown around just like sediment does. Ice is formed from compacted snow just like sedimentary rock does. You don't really get things like alluvial fans or anything like that, because in places that are classified as polar deserts are often covered in ice for all of or most of the year. Places that I would call tundra are not necessarily the same thing. Those things can get occasionally things like alluvial fans, but that's lower latitude. High latitude, everything's pretty much covered in ice, and so you can't really get a lot of the same things. A lot of the same features anyway. Okay. Any other questions about deserts? Yeah.
So we're a step.
Where are steppes?
We are a step.
We are a steppe. I'd say climatically, just going off of aridity levels, we are riding the line between desert and steppe. We're fairly high elevation, pretty arid, not as arid as some places, more arid than most. I'd say we're riding that line. If you want to go to a true steppe, I think I mentioned earlier, you can go to Mongolia. That's the classic sort of definition of a steppe. Colorado has steppes, things like that. Okay. Anything else?
Can soil erosion like make like desertification like faster?
Soil erosion?
Yeah.
Soil erosion is part of desertification to an extent. Desertification happens when an area over time receives less precipitation than it traditionally has. So the soil will change, right? The ratio of water, and then as less vegetation can grow in that soil, the ratio of organic content will change, right? Which is why in a lot of the places out here, if you ever talk to someone who is alive in the 20s, they'll probably tell you things look a lot different out here, right? Not just because they're putting up more buildings and more businesses and stuff, but because agriculture was way different. This place used to be a lot greener. Then Dust Bowl, and things haven't been the same since. So the soil will change as a result of desertification. It's kind of part of the parcel. What else? If there's no other questions, then we can move on and get Lab 5. We're getting Lab 5 today. You'll have your lab exam next week. Marquez, could you do me? Oh, never mind. I was going to ask you to poke Tony. Hey, Abigail. Abigail. Can you poke Claudia? Hey, we're going to talk about Lab 5 or Lab 5 now. Cool? Okay. All right. All right. Lab 5, topographic maps. Who can remind me what topography is? It has come up once in our class already. Topography.
Is it the study of elevation?
That's stratigraphy, huh?
This like graphing elevations or this
It has everything to do with elevations.
recording elevation, like
Yeah.
map.
Topography, which is impossible to say that word without thinking, you got to say it like a British gentleman. Topography, right? Let's have a conversation about the topography of over tea, you know? It's the study of elevation, but represented on a two-dimensional plane. Elevation is a three-dimensional concept, right? Depth, 3 dimensions. But how can we show it on a two-dimensional plane? That's topography. Maps are huge. We use maps in so many aspects of not only geology, but science in general, right? Here we have a satellite image. We can use this as a map, and we often do. Here we have a geologic map. Each one of these colors representing a different type of rock from a different time period. This is a topographic map, where each one of these little red lines represents a change in elevation. This is what you're going to learn how to read today. It looks confusing right now. It may still be confusing to you later, but you will know how to read them. Okay? This is a topographic map of our community. Look, here's Odessa, there's Midland. 2 years ago, I pulled this image up, and I had a student in my class, sat over there, who was like, how do you know where I live? I was like, what are you talking about? He was like, your marker is exactly on my house. It's like, I promise I'm not stalking you. That was an accident. I literally just picked a random spot between Odessa and Midland. It was weird. But here's Odessa, there's Midland. Do you see topographic lines, those red lines that I said represented changes in elevation? Do you see them anywhere? You do? Where? Anyone see them? There are a few, I promise. Like right here? Oh, that's bottom left, I guess. Like over here? Yeah, there are a few over here and over there. There's one here. There's one there. Look, this one says 3,000 on it, right? Yeah. Everywhere along this line is 3,000 feet above sea level. That's what that means. Look at the distance between these lines. We don't have much elevation change here. It's pretty flat. I think we can all agree on that, right? Let's look at a different picture. This is Earthquake Lake, Montana. Look at how close these contour lines are. Ah, look at that. We have made a connection. The closer our contour lines are, the steeper our slope is. Remember, each contour line represents a change in elevation. So if I have a lot of lines representing change in a smaller area, there must be more change over that distance, right? So the closer my lines are, the steeper my slope. The further away they are, the more gentle my slope. You can actually see that in this picture too. So this is a topographic map of Earthquake Lake. This is a satellite image from a slightly different angle, but I'll show you how you can compare these in a second. A little bit of backstory here. Earthquake Lake was formed in 1959. There was a 7.5 earthquake in Montana, caused the entire slope off the side of this valley right here to collapse into this valley, completely cutting off the river that was flowing through that valley. Believe it or not, it wasn't called Earthquake anything before then, right? It's taken on that name since then because the valley proceeded to flood, fill up with water as this river backed up. It backed up all the way up the valley to the point where several towns further upstream were getting flooded out. People were being forced to evacuate. So the Army Corps of Engineers were dispatched down here, and they blasted a channel through this landslide for the water to get out. And so they were able to help save those towns. There is still a lake there that goes a fair distance up the valley, but it's not endangering anyone anymore. That's where Earthquake Lake formed. So here you can see steep sides, steep sides, steep sides, steep sides, steep sides, steep sides. That's the valley, right? This valley side and that valley side. But notice how once we get past the lake and past the landslide, we reach the bottom of the valley. You can see where it starts to flatten out, right? You can see that down here too. We go from very close contours, they're getting slowly further apart, and then finally, look at the distance between these contours. This is a very flat area. That's the flat area you're seeing down here. Yeah.
Why didn't they blast it more? Allow more fire?
This already took tons of TNT. I mean, you want to get rid of all that, where are you going to put it, right? Basically, all that they needed to do was make a path for the water to get out. The water is slowly removing more as it goes, but they just were worried about doing enough to save the towns. They don't care that there's a lake there. It doesn't matter. They just wanted to make sure that the lake didn't get big enough to threaten people. Okay? So you can see this in practice, right? So that's topography. You are actually, I lied. You're not only talking about topography, you're also learning how to read a grid system. 2 grid systems, to be specific. How many of you all have ever used a grid system? How many of you have ever used Microsoft Excel? You've used a grid system. How many of you have ever played Battleship? You've used a grid system, right? There are 2 designations. There is a column and a row. And each one of these columns and rows has some designation so that you can figure out which square you're talking about. Cell B8 in your Excel spreadsheet. A9. Oh no, you sunk my battleship, right? These are all grid systems. You're going to learn about two grid systems today. The first one is township and range. This is very relevant, especially if you ever plan on being a homeowner or business owner or landowner. Township and range is the grid system that the US government uses to distribute parcels of land to determine where locations of ownership are. I own my house and I own a very small amount of property. And I mean very small. Tiny front yard, tiny backyard. But my house and that very small amount of property occupy a unit within a township and range grid system. And I can go to the local county clerk and say, hey, what's the township and range for my home ownership? And I give them the address and they can look up and say, you are in blah, 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 blah. Okay? That's how we distribute land. So it's relevant for you to know this. Okay? Especially if you ever plan on building a business or something or owning a significant chunk of land. The other system is called UTM, Universal Transverse Mercator. It works the exact same way. It just uses different notations. Both of these are very common, and so that's what we're going to talk about today. Starting with township and range. Behold, the box. Within this box is a dot. That dot represents my car keys. I cannot find my car keys, but I know they are right there. Someone tell me where my car keys are. They're right there? Well done. Where is right there?
No idea.
They're in the box, but how big is that box? And can you tell me where in the box they are? The left side? Bottom left? That doesn't help me. Your car keys are somewhere in this box that we don't know the size of, and you can't give me anything more than the bottom left corner. No, they're not. This is why we need a grid system. Because this happens, Professor Hart loses his car keys, and none of you all can help me find it. I could offer you 1,000 points of extra credit right now, and you still couldn't tell me where that was. You still couldn't help me find my car keys. But we have a grid system, and the game changes. Now, where are my car keys? Look, we have rows and columns, each one of which has a designation. My rows are called townships. My columns are called ranges. And we differentiate them based upon their relationship, their distance, I should say, from what we call 0 points, 0 lines. Okay, so in the case of townships, our baseline, which represents 0, is right here, this slightly bolder one. In our ranges, the 0 line is called the principal meridian. And it's right there. Anything to the left of our principal meridian will be range something west. Why? Because we're assuming north is up. As a matter of fact, I've given you a north arrow to confirm that. Okay. Anything to the left is west. Why? Because to the left of north is west. Anything to the right is east, just like on a compass. Okay. Here, for our townships, our baseline represents 0. Anything above that baseline is north. Anything below it is south. Township X south. Township whatever south. Then we count those rows and columns and their distance from the 0 lines. So here is 0. 1 column to the right of my principal meridian is going to be range 1 east. 2 columns, range 2 east. 3 columns, range 3 east. Anything below my baseline, township 1 south, township 2 south, township 3 south, township 1 north, township 2 north, township 3 north, grid system. Easy, right? As long as you know what your 0 lines are, it's battleship, right? So now someone tell me where my car keys are. By the way, it's not 1,000 points of extra credit anymore. It'll be 500 now for you to find my car keys. But we're not done. Tell me where my car keys are. Where?
They're in Township 2 North, Range 3 West.
Okay, so they're in Township 2 North, Range 3 West.
South. South.
Okay, Township 2 South, Range 3 West. Who would like to confirm this? Yes, they are, in fact, in Township 2 South, Range 3 West. But now I'm going to tell you that each one of these boxes, each township and range, is 6 miles to a side. What, you don't feel like scouring 36 square miles for my car keys? No? No, what? At this point, it's a me problem. Well, 36 square miles is better than the undefined area that we didn't know before, right? We're making progress. But this isn't as far as we go. Let's follow down the rabbit hole a little bit more. I take that square, this square, Township 2 South, Range 3 West. I take this one square and I'm about to blow it up, okay? This is Township 2 South, Range 3 West now. That's what we're looking at, this entire thing. I have now divided it into sections, 36 of them. Anyone want to guess how big these are?
1 square.
Yeah, 1 mile to a side. Because it was a 36-mile square area, I divide it into 36 boxes. Now we count these in a really weird way, going right to left, starting 1, 2, 3, 4, 5, 6, down. 7, 8, 9, 10, 11, 12, down. 13, 14, 15, 16, so on and so forth. Why? No one knows. I'm kidding. Someone probably knows, but I don't, and the people that taught me don't know, and nothing that I can find really has a great explanation for why. Someone somewhere who came up with this system probably knows why. Best way I can figure it is so that 1 and 36 end up on the same column. Bless you. Okay? Okay, so now where am I? Where are my car keys? Section 30. Yes. That's a 1 mile square area. Is that a little more doable? You still don't feel like doing that? Wow. You really don't like extra credit, do you? Huh? It's a lot of work. The juice ain't worth the squeeze, right? Okay, so we are in section 30. Or I should say my car keys are in section 30. I'm going to make that even more specific. I'm going to take section 30 and blow it up. Okay, so we are now just looking at section 30. I've divided it into quarters. Okay, slice, slice. Northwest quarter, northeast quarter, southeast quarter, southwest quarter. And then I divide those into quarters again. Slice, slice. Now tell me where my car keys are. Right there. Southwest quarter of the southwest quarter of section 30, Township 2 South, Range 3 West. And now I can tell you, or you can tell me, where my car keys are within a 1/4 by 1/4 mile area. That's way better. It's still a lot, but it's way better.
0.125 square miles.
0.125 square miles. Right? It's pretty good. It's about the size of an average home lot in most places, I think. You don't want to search your entire house for your car keys? I think we've all been there. All right. This is township and range. Now, the way that we write this is from smallest notation to largest notation. So this would be southwest quarter, section 30, Township 2 South, Range 3 West, and that's how you would describe it. Now, I have good news. On your exercise, on your lab, I don't have the technology yet to let you zoom in as far as you would need to for sections. So all you have to do is tell me township and range. Don't worry about sections or quarters. Okay? You have, I think, 8 points on a map that you need to identify on a township and range grid, just like this one. All you have to do is say township and range. No sections or quarters required. Okay? But you understand how it works. Now for UTM, Universal Transverse Mercator. This is the international grid system. Okay? I put this on a map, and anyone in Germany or Holland or Australia or Taiwan or Tanzania can read it. Okay? Anyone who understands UTM can read this and understand it. Okay? It is in meters, not in feet. Bear that in mind. Yes. Science. Okay? Science uses the metric system. Now, just like with the other grid system we discussed, just like with township and range, we have columns and rows. However, each column and row has a distinction, has a name, based upon their distance from their meter distance from the zero line in both columns and rows. So here, for example, I have snippets from the top and side of that earthquake lake map I showed you earlier. Let's look at these. This line right here says 61,000 meters east. What does that mean? Everywhere along that line is 61,000 meters east of our zero line. Let's go to the next line. Yeah, it's not there. That's missing. Well, why? Well, because someone decided to put additional notation there. So we'll go to the next line to see what that number is. This one says 63, which lets us pretty accurately think of this one as 62, right? 61 to 63, the middle one must be 62. 63 what? 1,000 meters east. It only says 63 here. That's purely to save space. They only give you the whole number once, usually in the corner of the map. And then they require you to interpret it after that. 63,000 meters, 64,000 meters, 65, 66 across the top and bottom of your map. Then we've got the sides. Here's our whole number, 68,000 meters north, meaning that everywhere along this line is 61,000 meters north of our zero line. 67, 66, so on and so forth. So if I asked you to tell me where the location of something was on this map, you would give me two numbers, the column and the row. And you would have to tell me all of it. Don't just say 63 by 67. 63,000 meters east by 67,000 meters north, for example. And that tells me which box I need to look in for that feature. That's UTM. I'll show you another example here in a second. Any questions about that before I talk about contours a little bit more? Okay, contours. Elevation. Elevation is relation to sea level. I say that very carefully. I use that wordage very precisely. It is not above sea level, although that's how we typically think of it. It is relation to sea level. What is 100 minus 200? Negative 100. Is it still a number? Yes. Simply one with less value relative to zero, right? Elevations can be below sea level, and in fact, they will be on this assignment. Bear that in mind. You have your contour intervals, which are these dark red lines, which usually have numbers on them. This one says 8,000. This one says 9,000, right? This one says 9,600. This one says 8,800, right? So between boom, 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 those 5 lines, there are 4 spaces between 9,000, between 9,000 and, wait, hold on, is that 9,000 or 9,600? I can't, it's 9,600, okay. I was like, wait, that seems off. 9,600 and 8,800, what's the difference in elevation? 800. Between this line and that line, there is an 800-foot drop, but there are 1, 2, 3, 4 spaces between that. What is the difference here? 200, 200, 200, 200. And look, there's 1, 2, 3, 4, 5 spaces between each of those, which are represented by how much difference? This is 200, 5 spaces. 200 divided by 5. 40. 40, 40, 40, 40, 40, 40. So if I ask you what the elevation is of this point, sorry, that point, that was a bad example because it landed on a dark line, okay? This point, you would say, okay, well, that's 9,600. So let's subtract 200 here, so 9,400, and then 40 until we reach that. 2, 3. That's 120 feet I need to subtract. So 9,400 minus 120 9,280, right? Did I do that right?
9,240.
I subtracted 120 from 9,400. It should be 9,280.
I subtracted 400 and then added 2 lines.
Yeah.
240.
Yeah, 9,280. We're saying, yeah,
They're all 40.
they're all 40s. Yes. I was like, wait, what's going on here? 9,280 would be the elevation at that point. That's how these work. It is some math. I apologize. I told you there wouldn't be much, but there would be some. But I'd give you all the equations for it. And I just did. You literally just count it. Okay? Now, here's something else to bear in mind. Out of the maps you can choose, there are 2 maps you can choose for this exercise. Hoquiam, Washington, and Monterey, California. Okay? Both of those have ocean on them. Now, these elevations are in feet. Ew. But what happens when we get in the ocean? Ocean is not America. Ocean is international. Ocean is in meters. Bear that in mind. I do give you the equation to convert. So if at any point you need to deal with an elevation that is in the ocean, which, by the way, sea level represents 0, so elevations in the ocean will be below 0. Yeah, remember that too. You'll need to convert from that meter number to feet or from feet to meters. It doesn't really matter to me which one you give me if you're comparing the two. Just if you're only dealing with land elevations, do it in feet. And if you're only dealing with ocean elevations, do it in meters. If there is a question, which there is, that requires you to compare both of them, you can do it in either feet or meters. I'll take that. Talking about what we mentioned earlier, these 2 boxes are the exact same size, but I put it over here. I've got 19 intervals here, contour intervals. I put the same box over here, and I have 10, meaning that I have a difference of 9 contour intervals over this same distance that I do here. This is steeper than that one is. The slope is steeper than that one. That's how that works. And here's a representation if you wanted to see that. Water. When streams or rivers are represented on a contour map, the contours will make a V shape. Because wherever your water is, it is digging into the rock. It is weathering that rock away faster in that location. And so, as a consequence, my topography is going to V in that direction. And so when I see this kind of V shape on my topographic map, I'll know that I just follow that V shape towards the source of the water. The V's point in the direction that that water is flowing from. So let's do a practice. In what location, using UTM coordinates, does Dead Man Creek start? Well, first we need to find Dead Man Creek, right? So let's see, I'm going to find, there it is. Water represented in blue, and I found the one labeled Dead Man Creek. Now, how do I know which direction it's going in or coming from? I look for the V's. Camera, stay with me here. There we go. Look for the V's, right? So I can see my contours are V'ing in this direction along that body of water. So I'm going to follow the V's. I'm going to follow that direction, that body of water, until I come up here and wait, where did the V's go? Wait, where's my blue line? My blue line became a dotted blue line and then disappeared, and my V's are gone now as well. That must be where Dead Man Creek starts. And so we're right somewhere in that circle. So now to give the UTM coordinates, all you have to do is tell me this square. Here's the trick. How do you know if it's in, or how do you know if you use this number of that line or the number of this line? It is in this square, and this line is represented by 62,000 meters east. It's going to be in this column. So this is at all points going through this column, everywhere through this column until I reach this line, it is 62,000 and something meters east. Even up until 62,999 meters east, it is still in that number category. You don't have to give me anything other than 62,000 meters east, because this is a 62,000 meters east column. What about the row? Well, here we go. 67, 68, 69 is up there somewhere. But this row, everywhere in this row is going to be 68,000 and something meters north. So to tell me where Dead Man Creek starts, you would give me the location, the coordinates of this box, which is 68,000 meters north, 62,000 meters east, and I'll be able to find that box and give you your credit for answering that question. Clear? Good? Yes? We happy? Are we happy it's not more identification? Yeah? Good. All right. Your maps will look like this. This is your Monterey, California map. This is your Holcomb, Washington map. Now, I don't expect you to just use the ones on the PowerPoint. Matter of fact, please don't. For those of you that are taking the class in person, camera, stay with me, baby. Come on. There we go. For those of you that are taking the class in person, I have actual copies of these maps, which Claudia has set camp up on over there. That's okay. I'll get those. And for those of you that are taking the class online, or those of you that are taking it in person but want to work on it at home, I have HD 4K copies of these uploaded on the Blackboard page. It may take a little bit for you to download them because they are high quality, and depending on the quality of your internet, they can take a while. Like if you try and download them here in this classroom, it would take forever. But luckily, if you're in this classroom, you have the hard copies. For those of you doing this online, make sure you have a good internet connection. Do not preview the maps in Blackboard to try and look at them, because if you zoom in, it'll get blurry. But if you download them and zoom in, you'll be able to zoom in to the max and still read all the letters and the words, or the numbers. Any questions about this lab before we get started? Alrighty then, I will end the recording here, and we can begin.